Yeah, thank you very much. And again, thank you to the Newton Institute for the generous support, the organizers for inviting me. It's really refreshing and nice to see everyone in person again. So I'd like to talk about thermo-compositional convection in dynamos in rotating systems. And this is work that we've done with Louis Silva and James Matter. It was supported by the Leverhulme Trust. Our project finished 3 years ago, but I haven't had the chance to report these results yet, so I thought it might be of interest. Right, and so the motivation for considering this problem, of course, is that convection in the Earth's outer core is driven by both thermal and chemical composition gradients. And the chemical component of the buoyancy force is estimated to be large, about 80% probably of the buoyancy force. Double-diffusive effects, as we heard this morning, are also important in other planets, in particular Mercury, Venus, Jupiter, and Saturn. However, global simulations of core convection and dynamo often adopt a single diffusive approach, so the codensity formulation. The codensity formulation, however, is not properly account for differences in diffusivities, differences in boundary conditions between the heat and concentrations, and different sink source distributions of heat and concentrations. And so there have been a range of previous papers that consider two separate equations, one for the concentration and one for the temperature. However, we thought that there is more to be learned in this problem. So it is our goals were to assess the possibility of dynamo actions in stably stratified backgrounds, in particular the semi-diffusive and the fingering regimes, assess the differences in dynamos and convection in the thermally and chemically dominated overturning regimes. And beforehand, of course, it was necessary to map out the thermo-compositional regime boundaries in the parameter space. And so in my talk today, I will start first from this last problem. And we will map the thermo-compositional regime boundaries by considering first a very simple model, so the model of rotating cylindrical annulus with sloping bases that I'm sure we are familiar with. So in here, the centrifugal force acts like gravity, just in the opposite direction. And the modification that we make is to consider a two-component fluid. So to simplify the model further, we make the narrow gap assumption. We assume that this gap here is sufficiently narrow. We use the Bose-Einstein approximation. Density is constant everywhere except the centrifugal force, where it depends on temperature perturbations and concentration perturbations. Small inclinations here at the sloping boundaries, rapid rotation, and we average the equations in z direction. So when we do that, all of that, we come up with a set of three equations. The first one is the momentum equation written for a stream function for the velocity field, and then the equations for the temperature deviation and the concentration deviation. What we use in here is Dirichlet boundary conditions, so fixed temperature and concentrations at the x boundaries, so here and here, and stress-free for the velocity field, while we are periodic in y direction. So with the following scales, there are 5 non-dimensional parameters. So this eta stars measures the ratio of rotation to viscosity, and so it's our rotation parameter in the problem. The Prandtl number, so the Prandtl number is the viscosity versus the thermal diffusivity. The Lewis number is the ratio between the thermal and the concentration compositional diffusivity. And we have 2 Rayleigh numbers that we control the driving due to the buoyancy and the concentration. And to map the region of instability in the parameter space, or the simplest thing that one could probably do is to consider linear stability analysis in normal mode. So we make the usual Fourier ansatz. And when we linearize the equations, we have this 3x3 matrix eigenvalue problem for the complex eigenvalue and for the eigenmodes. And so this has 3 eigenmodes, because it's 3x3, which I have plotted here as a function of the Rayleigh number. So I'll consider fixed parameter values, except for the Soluto Rayleigh number, in which I have a positive and a negative value, so stabilizing and destabilizing. The destabilizing is in red, the stabilizing is in blue. And there is also a range of blue curves which correspond to the purely thermal case where we don't consider the compositional equation. So the purely thermal case gives rise to these two eigenmodes which look like sort of a supercritical pitchfork bifurcation in a way. And we see that the compositional convection also has similar modes which are modified a little bit with respect to the purely thermal one, but there is an additional double-diffusive mode that appears here and has a very small growth rate. So on the y-axis I have the growth rate. Although if you zoom this out, you will see that there are actually regions in terms of the thermal Rayleigh number where it becomes unstable. And interestingly, this region is separated from the main region of overturning convection. All right. Well, how do we use this to map the parameter space? Well, in order to do that, we need to sort of construct the neutral surfaces for the problem, and we do that by setting the growth rate equal to 0 and obtain the following dispersion relation from the characteristic equation of the eigenvalue problem. Well, this defines a 5-dimensional neutral hypersurface, and you can express the critical value of any parameter of the function of the remaining 5. So I'd like to think here of the thermal Rayleigh number as a function of the Prandtl number, for example, rotation rate, the Lewis number, the Soluto Rayleigh number per given azimuthal wave mode. And so again, the blue and the red curves are sort of different to different sets of fixed parameters. Blue is a stabilizing Soluto gradient, and S is this, red is the destabilizing. So what we find is that convection is then determined by 3 different values of the Rayleigh number in order to characterize the onset. For instance, if we look at this cross-section of the hypersurface on the plane of the critical Rayleigh number, thermal Rayleigh number versus the mode, the azimuthal mode. Say at a fixed azimuthal mode, if you increase the thermal Rayleigh number, there will be a critical value where one enters a region of instability. If you increase the thermal Rayleigh number further, well, then you reach a region of stability again. So the flow will be stable to small perturbations. And if you increase your Rayleigh number still further, there will be a third critical value where you enter a regime of overturning convection. And, well, one can trace this in terms of the other parameter cross-sections, sort of the Soluto Rayleigh number, the Prandtl number, and so on. Right, and in this slide, I'd like to illustrate that this sort of linear picture persists in the non-linear regime. So if you consider now finite amplitude convection with all modes competing, well, and again, let's concentrate, for instance, on the red case. So in the red case where the Soluto Rayleigh number is destabilizing, I mean, there is a region here of instability, which then disappears as you continue to increase the thermal Rayleigh number, and then you enter another region of instability sort of further on in terms of Rayleigh number. So these here are the critical wave numbers where this the onset happens. Right, how does this translate to spherical shells? So in spherical shells, we consider electrically conducting, self-gravitating two-component fluid, like in this configuration, rotating with a constant angular velocity again, with respect to the vertical axis. Again, in the Boussinesq approximation. And we have the familiar governing equation, so I'll just point out, so that these are the equations now where I have included the magnetic field, magnetic induction equation. And there is a slight difference in non-dimensionalization from the previous problem, where I've written non-dimensionalized now in terms of the Schmidt number, which is the ratio of the viscosity versus the concentration diffusivity. So then that the concentration equation and the temperature equation are really symmetric, so they look similar to each other. So just to have the Prandtl number and the Schmidt number in the corresponding places. Right, another thing that I might mention is some of the results there written in terms of the Coriolis number, which is 2 over the more familiar Ekman number that many models use. Stress-free boundary conditions, again, fixed temperature and concentration at the outer and inner surface. And in the cases with magnetic field, we consider potential magnetic field at the exterior. All right. A similar step before we can proceed to actually look at dynamos and convective solutions, we would like to see now, again, the linear stability picture and see where the different regimes of convection will appear. So in order to construct the overall critical curves, we need to construct the lowest envelope of the critical curves for all azimuthal wave numbers competing. So the azimuthal wave numbers, spherical harmonics are in M. And so these critical curves are in turn lowest envelopes for the structural eigenmodes. So this is how they look. But we'll remember that they were triple valued in the linear analysis in the annulus. So what we have done is to reparameterize our Rayleigh numbers into an effective Rayleigh number, which is the square root of the sum of squares of the thermal and the compositional Rayleigh number, and a corresponding mixing angle. And so this transformation is very similar to the transformation that we'll do between Cartesian and polar coordinates. And when we do it, the advantage of it is that in terms of the mixing angle, well, the critical curves become single valued, so one can then find a lowest envelope. And so this is a picture for some fixed values of the parameters, of how different modes and their structural eigenmodes compete to form the black curve, which is the overall critical curve in that case.
In this case, both Rayleigh numbers always positive?
In this case, no, the Rayleigh number is not always positive. I mean, so this would correspond to thermal Rayleigh numbers that are negative, and so on. So that's actually on the next picture where I'm unfolding it and writing it. So this is the curve in this effective Rayleigh number and mixing angle, and this is the same curve in the plane of the compositional Rayleigh number and the thermal Rayleigh number. And so we're identifying regimes of compositional convection as A, sort of the semi-convection regime would appear here, where the compositional Rayleigh number is negative, so stabilizing, and the thermal is positive, so destabilizing. The fingering regime of convection will appear in this region, sort of for positive compositional Rayleigh numbers and negative thermal Rayleigh numbers. Right. The other parameters are fixed as follows. So we have Prandtl number equal to 1. The Schmidt number is 25. So there is a significant difference in the diffusivities. The rotation of the tau, the Ekman number is 2, 10 to minus 5. The aspect ratio is similar to the Earth. So in order not to lose the boundaries between the different thermocompositional regimes, I've stayed fairly close to the linear onset, so it is weakly nonlinear. And the magnetic Prandtl number in the Dynamo simulations further on is selected as large or as small as possible as necessary to generate dynamos. So there is no particular trick there, yeah. And the red dots that I'm showing in here are the finite amplitude simulations that we've run. So in order to see what happens in the different regimes, basically selected to run sort of cases with constant thermal Rayleigh number or constant compositional Rayleigh numbers. And the simulations largely, close to the critical curves, largely confirm the linear analysis. So these are now time and volume averaged kinetic energy density components and Rayleigh numbers, and Reynolds numbers, excuse me, as a function of the two Rayleigh numbers. fixed along those vertical and horizontal lines. And say if we consider one sequence, say the sequence C, in which the Rayleigh number is fixed here to the compositional Rayleigh number is fixed here to this value. We see, again, the fingering regime, which is unstable for some values of the thermo-Rayleigh numbers. Then we're region of stability again, and then we're in a region of instability where we have compositionally dominated overturning convection and thermally dominated overturning convection. And one thing to note is that the flows in the semi-convection and the fingering regimes are rather slow, so the amplitudes, the kinetic energies of them are some orders of magnitude smaller than you would have in the overturning regimes. Right, and what I'd like to do now is to illustrate some planforms and patterns of these convection and dynamo solutions. So I'll do that by looking at plots of the differential rotation in this part of the meridional plane and the meridional circulation here to the right. And I also look at the radial velocity on the spherical surface and midshell and the equatorial plane in here. And so this is along one of the horizontal lines where we keep the compositional Rayleigh number fixed, but we increase the thermo-Rayleigh number. Or the first picture is a pattern of convection in the fingering regime. So what we have here is somewhat narrower downflows and wider upflows. Or there is a large deviation from the cylindrical profile of the differential rotation. So differential rotation looks in this particular way. And the pattern for small wave numbers dominate, like predicted by the linear analysis. Increasing the thermo-Rayleigh number. Oh, this is the compositionally dominated overturning convection regime that I've denoted by C in the previous graph. So in here, we have narrow convective columns. The differential rotation is of thermo-wide type. And I mean, I would explain this by the similarity between the compositional and the temperature equation. So the compositional equation works more or less like the temperature equation with a large Prandtl number. So the Schmidt number is 25 in here. That is why we characterize this as a thermo-wind regime. And here we have large wave numbers, so there are many cells around. Increasing the Rayleigh number still further, then one jumps into the thermally dominated overturning convection regime, which is very familiar from previous simulations. So what we have in here is thermo-Rossby waves, which take the form of this convective columns arranged in a cartridge near the equator. And as you drive things stronger and stronger, well, then there is the familiar transitions from laminar to chaotic states. One can obtain polar convection and sort of localized convection at higher Rayleigh numbers, relaxation oscillations, and so on. So there is some delay between the clicker and the slides. So I want to be in here. Yeah, I want to be in here. So I'd like to then demonstrate a pattern of convection in the semi-convective regime A. So this is the first column here, the first case, where one would observe that the pattern of convection consists of wide diffuse upflows and downflows, sort of largely similar in length scale. There is, again, a large deviation from the cylindrical differential rotation profile. This looks very similar to the differential rotation in the fingering regime, but it is opposite in direction. So this was retrograde in the case of the fingering convection regime. And here, very small wave numbers dominate. And again, in this particular sequence, when you increase the thermo-Rayleigh number, you then reach ultimately the other two regimes of overturning sort of chemically dominated and thermally dominated convection C and B. And what about dynamos? So now, I mean, that we know where the different regimes of convections are. What I've done is to increase the magnetic Prandtl number sort of appropriately to obtain dynamo solutions. Well, we weren't able to find any dynamos in the fingering regime D, but we found a dynamo, or not dynamo, sort of a number of dynamos that all look similar to this one, this typical case, in the regime of semi-convective flow. So because the magnetic Prandtl number here is huge, so 300 is a very large magnetic Prandtl number. The case develops very slowly, but we followed it for over 2 magnetic diffusion times to make sure that it's not transient. And the dynamo shows very little variation in time, so it mostly stays like this. So the new plots that I'm showing are those two. These are the familiar convection patterns. So in here, I've plotted the B phi component of the magnetic field and the poloidal field lines in the meridional plane and averaged in azimuthal direction. And this is a picture of the radial magnetic field on the surface of the spherical shell. And what we see is that the magnetic field is strongly dipole-dominated. It does not change much. And the toroidal field in particular is concentrated here at the outer part of the spherical shell near the equator and on the tangent at the tangent cylinder. Right. A thermally dominated overturning regime is very familiar, so we have a large database of simulations from previous studies. Well, things look similar indeed. So in this example, at these particular values of the parameters, what we find is an example of a regularly oscillating quadrupolar solution. So the two lines, so this row and this row, show two snapshots at the beginning of a period of oscillation and at the middle of the period of oscillation. That is why the polarity of the magnetic field is reversed. So we have here the red spot on top and here the blue spot. Otherwise, the patterns between that picture and that picture look very similar. Like the way in which the magnetic field affects the convection is largely an effect on the differential rotation. So the differential rotation also cycles through the changes through the cycle between the sort of more geostrophically oriented and this broken pattern of flow. Yeah, here's a dynamo, actually two dynamos, two different dynamos in the first row and the second row in the compositionally dominated overturning regime with these parameters. Again, the same plots that I'm presenting here. So the solutions appear similar to large Prandtl number dynamos in the thermally dominated regime. And you can think of this as basically the similarity between the compositional equation and the temperature equation, where the compositional equation now is dominating. And it has a large Schmidt number, sort of large Prandtl number. So in this regime, then, we have a sort of magnetic fields that evolve very rather slowly. And the dynamos are sort of quasi-static dipolar dynamos with relatively weak differential rotation. So this picture then pretty much stays like this in time. Right, and yeah, it is getting about time for lunch, so I think I will proceed to my conclusions. What I've presented is a diagram of thermo-compositional regimes in the parameter space. We've demonstrated some typical weakly supercritical convection and dynamo patterns and planforms. We were not able to find dynamos in the fingering regimes, but the dynamos in the semi-convection regimes exist. They're rather weak and require very small magnetic diffusivity, so large values of the magnetic Prandtl number to operate, which is somewhat disappointing. The dynamos between thermally and compositionally dominated overturning regimes are similar, which perhaps justifies the use of the co-density formulation. However, the advantage of using a double-diffusive formulation is that one can explore, for instance, the boundary between the two regimes, where the properties of both the magnetic field and convection change very significantly for small change in configuration, for small change in the Rayleigh numbers, sort of the thermal and the concentration Rayleigh numbers, which then allows the possibility, for instance, to explore interesting dynamics or perhaps find periodic reversals. Right, and the results that I've discussed are sort of a summary of these here papers. And I'd like to also acknowledge again the support of the Leverhulme Trust.
So thank you very much. Time for questions, Chris.
In your semi-convection case, I see you needed a very large PM. That's because your velocities are very small.
Yes, that's right.
Is there any prospect, do you think, of actually getting a scaling law as to how the velocities actually vary as a function of the heat flux? Because the critical question is are the velocities large enough to drive a dynamo in a realistic situation?
That was indeed disappointing. I mean, I guess the velocities in that case will remain to be small. And we just haven't sort of run enough other simulations apart from this particular value for the Prandtl number. So that, I mean, sort of all other parameters were fixed, we're only varying the Rayleigh number and the two Rayleigh numbers, essentially. But it is conceivable that...
do you need to work out how
yeah.
do you need to work out how the velocity scales with the other parameters, because it may be that actually the velocity starts to go up as when...
Yeah, that was the hope, indeed.
Yeah.
That was the hope.
Yeah.
In your fingering regime, the scale seemed quite large. I didn't see anything that I would have called a finger.
No. No, I mean, I wouldn't see anything that I call the finger, but that is the configuration that is basically attributed. So in the fingering regime, this is this D here, is where you have thermal Rayleigh number positive, so the stabilizing, and the compositional is stabilizing. There have been some estimates, sort of instability criteria in non-rotating unbounded gradient layer model is what is called. So in there, then the stability criteria defined in this sort of stability density ratio parameter. And I mean, we've looked into that. So this is then the stability criteria for overturning convection, which is then plotted this little green lines I didn't comment on. So the fingering regime is between these two green lines. That is why, I mean, I've we've identified that as the fingering regime. But this is, I mean, it is in our situation, it is affected by the boundary condition. Like, for instance, in the unbounded models, there are no boundary conditions. You assume that you're far away from that. There is an effective rotation as well, so that's how it appears.
Just seems a bit surprising. If you don't have rotation, you have
that's
fingers.
how. I mean, there is some sort of very weak indication of similarity between upflows and downflows. Let's just wait for this to come back. Yeah, so these are thinner than these.
They're very big scale fingers.
Yeah.
Sorry.
Any other questions? Well, if that's not the case, let's thank Radostin once more.
Thank you.
So we break for lunch and reconvene at 1:45.